Thanks very much for having me. So I'm going to try to get us back on schedule a little bit. I'm going to talk about 2D silicon and germanium nanomaterials for biological applications. So I do a lot of work on nanocrystals. I'm obviously not the only one in the world. This is a pretty active research area for the last probably 25 years or so. The idea is making colloidal nanocrystals of various types. A lot of times semiconductors, if we're thinking about light emitting properties for imaging. And then the nice thing about these materials is they're small, they're similar to the size of macromolecules. You can functionalize their surface and you can tune their optical properties. So I'll show a little bit of data on multiplex imaging. And if we think about multiplex imaging or targeted doing imaging using different targets with different colors, we can look at these objects by changing the color of what's binding to them. That's one fundamental theme I'm going to talk about. And then another fundamental theme is the optical window for imaging. So looking at the kind of how transparent biological systems are or how transparent people are. There's a window of transparency in the near infrared, in the kind of red to near infrared, and there are a couple of regions, near infrared 1, near infrared 2, that you can target. I'm going to talk about silicon and a bit about germanium. And the nice thing about silicon compared to cadmium selenide is it doesn't have cadmium. Cadmium's a toxic metal. So for in vivo imaging, that's a problem. Silicon also emits in the near infrared, but silicon requires blue photoexcitation because of its band gap. So I'm just going to show briefly some data about how you can use silicon quantum dots for imaging. You can do 2-photon absorption. So you hit the nanocrystals with a high intensity laser with red photons to get 2-photon absorption. So it's essentially similar to photoexciting with blue light, but you're actually using red photons. And the nanocrystals then will emit. And silicon has a fairly decent 2-photon absorption cross-section. I'll share some data in a second. So for silicon, one way of making silicon quantum dots is to take this molecule, hydrogen silsesquioxane, heat that up in a furnace above 1100 C, you get silicon and oxygen disproportionation. So you crystallize silicon quantum dots in an SiO2 matrix. You etch the SiO2 matrix away, liberate hydrogen terminated silicon, and then you can passivate those nanocrystals. And we've worked on a variety of different passivation schemes. We can, depending on the functional group that's exposed on the nanocrystals, they can be dispersed in water or organic solvents or polar organic. So we've developed methods for doing low temperature passivation, making them water dispersible. So we can take these water dispersible silicon nanocrystals that emit the red towards the near infrared region and use 2-photon excitation and do imaging. And in addition to that, do multispectral imaging using the long photoluminescence lifetimes of the silicon. So silicon as a semiconductor has an indirect band gap. So it really doesn't emit light as a bulk crystal. When you make nanocrystals, you sort of change the selection rules a bit, and electron hole recombination, radiative electron hole recombination begins to become allowed, but it's still an indirect band gap, and so the lifetime is relatively long. So these are some data where we've labeled some cells with silicon nanocrystals and 2 dyes of different color. The dyes have short photoluminescence lifetime, nanosecond, and the silicon quantum dots have microsecond lifetimes. And what you can do when you're imaging is you can look by the time signature. So this is a pulse light source, and you can essentially look only for the long lifetime emission. And since the dyes have short lifetime emission, you can identify the silicon quantum dots which might be emitting, in this case, red, from a red dye. So the same color, but two different lifetime signatures. So this is one way of doing multispectral imaging with silicon quantum dots that's pretty unique. Most quantum dots have short lifetimes, 10, 20 nanoseconds, and you can't really use this technique for it. The other thing that time-gated imaging is good for is getting rid of the autofluorescence background in biological media. So it's another powerful capability of silicon. So those are silicon quantum dots. We can use this to essentially this imaging technique to see where the quantum dots go within a cell. So do they go to the nucleus? Do they go into different kinds of compartments in the cell? And so we've studied that a little bit. Most of what we've done is just making the materials, demonstrating it's possible to do time-gated fluorescence lifetime imaging with 2-photon excitation with silicon. But a next step is to think about where do those quantum dots go, and then how does shape affect that. So germanium is another indirect bandgap semiconductor material that if you make a quantum dot, it can start to emit light. Its light emitting properties are much less understood than silicon. It's more difficult to get light emission from germanium quantum dots that are made synthetically, but we want to be able to do it because the germanium has a lower band gap than silicon. The light emission is pushed a little more to longer wavelength into the near infrared. So what we've been doing is playing around with different syntheses. I'm going to show you the results from a synthesis using germanium dibromide and olelamine, and we can make germanium quantum dots using this method colloidally. And what's interesting about these dots is that they form these triangular prisms, and that shape turns out to be important for the light emitting properties of germanium because these dots are actually fairly bright. So the photoluminescence quantum yield of the germanium quantum dots is about 1 to 2%. The emissions out in the red. You still have what looks like a large Stokes shift with the photo excitation. So in that way, it's similar to silicon. And the photoluminescence lifetime of these quantum dots is long. So it's microsecond. Germanium, as I mentioned, has an indirect band gap. So you see that just to make sure or get an idea of what the light emission is coming from. Is it a quantum size effect or something related to surfaces? We need XPS to look at the oxidation. And these quantum dots have a little bit of oxidation, but not that much. We can shift the emission a little bit by size. So those are different reaction temperatures and different reaction times. But for the most part, these dots are emitting pretty squarely in the red with long lifetimes that have a slight size dependence. And so we've looked into the mechanism for the light emission from these dots. And what we think is happening is that in the synthesis, these dots get their triangular prism shape based on stacking faults. And those stacking faults we see in all the dots. And our idea is that those stacking faults create some strain, some lattice strain within the germanium. So you have a quantum size effect and some lattice strain that shifts the band gap, maybe not to become totally direct, but almost direct. And so the two reasons for the light emission are the size, the quantum size effect, and also the strain within the dots. Okay, and so we made some other spherical silicon dots that don't have this strain. And if you plot the exciton energy versus size, you can sort of map some what you'd expect with the effective mass approximation. But for these dots made with germanium dibromide, their energy of emission is a little higher than expected based on just size. So another confirmation that there's something going on in those dots. So those are interesting. They're I would call them 2D materials. They're sort of 2D, 3D little triangular nanoprisms. these are the silicon nanosheets I'm going to show you are truly 2D. So what we do is we take calcium silicide, we carry out a reaction in hydrochloric acid to form siloxane. And this siloxane is very interesting. It's got this layered structure. And then what we do is exfoliate that and with some sonication or just a bash shaking. And then what we do is a liquid cascade centrifugation to separate these sheets by size. Siloxane, bulk siloxane is photoluminescent. It emits green light, and these nanosheets that we make emit blue light. An interesting thing about the siloxane sheets is that they're very unstable under the electron beam, so it's difficult. I think these is the only image I know with essentially atomic resolution of siloxane, and it was extremely difficult to get this image. We got it out at Diamond in the UK, very low accelerating voltage, and if you look at the crystallinity, as soon as you hit it with the beam, the material starts to become amorphous. So the very beam sensitive materials. So when you do this, the sonication process, so high energy sonication to exfoliate the siloxane, you can make these sheets of varying diameter and then separate those with the liquid cascade centrifugation. And those sheets have size dependent light emission. So siloxane emits green, but these sheets emit blue light, and the smaller they are, so that 2K, 3K, that's the centrifugal speed basically. So the higher that is, the smaller those sheets are that we're isolating. So we have these sheets. We've looked at them to try to understand a little bit more about their optical properties. The sheets themselves, they're difficult to obtain without significant oxidation. So the green emitting material, you can do it if you use like NMP as a solvent to prevent oxidation, even though the material is still slightly oxidized. Siloxane has some oxidation. But when you do the sonication in the air to make these smaller sheets, there's more oxidation. And I'll just show these data real quick. So this is some EELS data of individual sheets, and using EELS, you can get a lot of information about how much these siloxane sheets or the silicon nanosheets have oxidized over time. So the siloxane nanosheets are really interesting because they emit light, not too difficult to make, but they're very sensitive to oxidation, which tends to really blue shift the emission. And if that blue shifts too much, it becomes a bit of a headache in terms of biological imaging. So anyway, those are some examples of 2D germanium and silicon, and a little bit of data about silicon quantum dots and cellular uptake and multimodal imaging, multispectral imaging, multiplex imaging, I guess you'd say, using the lifetime of the emitters. And I had 3 students who basically gathered all that data. So Jung Chul on those germanium prisms, Dorothy did all the work on the silicon dots with the multiplex imaging, time-gated imaging, and Tusi Shah did the silicon nanosheet work. So thank you very much.
Thank you very much, Professor Brian. I got a question in the chat. Is siloxane surface oxide or bulk oxidized? I hope I pronounced that right.
Hello.
Hi. Yes.
So hi. So my question is like, it's not, is it surface oxidized or is it bulk oxidized when we are talking about the oxidation of siloxane? That's my question.
Yeah. So the siloxane itself, when you react the calcium silicide with HCl, the silicon atoms are being functionalized with hydroxyls. They're being hydroxylated. So in that in that sense. So every silicon atom is terminated by either a hydrogen or a hydroxyl group kind of alternating. And then when you exfoliate these, when you peel these layers apart, then you expose all of this surface, and that's where you can get additional oxidation.
Okay.
You can either oxidize where you oxidize the hydrogen, like silicon hydrogen bond, but a lot of the oxidation is bond breaking between the silicon. So you have oxygen insertion between silicon bonds.
Okay, okay. So basically when you're etching it with HCl, it's like the dangling bonds are saturated. It's passivated by hydrogen bonds. But
Yeah,
basically
it's
when you're doing LP, you are exposing the surface again. So then you are saying the oxygen is coming, is it?
Yeah, when you do the HCl, you get some hydrogenation. So some of the silicon is terminated by hydrogen, but also silicon atoms are terminated by hydroxyl groups. So in that HCl process, you do get that sort of oxidation. But within the bulk siloxane, the silicon's still relatively protected to oxygen exposure and water. And so you don't get this oxygen insertion into the silicon until you exfoliate, and then you have to be careful with the degradation of the material at that point.
Okay, I have one small question as well. I thought the time is enough. So the question is like, so this the bulk material which you're using is non-layered, right? That's why you're doing etching to make it kind of layered, right? And then you're doing LP to achieve the exfoliation of nanosheets. So my question is like, so the bulk is, the starting material is it crystalline, but then you are getting the end product as amorphous.
Yeah, so the starting material, calcium silicide, is a layered material. So calcium silicide is kind of like silicon, calcium, silicon, calcium. And what you're
so what
doing
is the bonding between calcium and silicon? Is I assume is not, is it van der Waals? I don't think so, is it? It's stronger than that.
No, it's not van der Waals.
Right, so
yeah,
it's not
stronger,
a van der
like
Waals layered material. Yeah, it's layered, but it's not necessarily a van der Waals material. So we can't say it's a 2D material. Yeah, we can't say it's a 2D material then, because by definition, when we say 2D layered materials, we are talking about van der Waals interactions. So
I actually wanted a comment on that is that in general, 2D materials can be larger class than just van der Waals materials. Because, for example, MaxScenes is a very large class of 2D materials, which is not van der Waals bonded. So yeah. I wouldn't restrict it to that.
But MaxScene is like, it's actually etch product of Max, right? So Max is actually not a 2D material, but MaxScene is, because the sheets are electrostatically bounded when you remove the A atoms.
That you're correct.
Yeah. So you can do LP of MaxScenes to actually get nanosheets, but you can't do LP of Max to get nanosheets. That's what my question is. So similarly, he is also doing etching of calcium silicide to take off the layers of calcium to make it actually electrostatically layered kind of structure to further do the liquid phase exfoliation to extract the sheets. But my question was different. My question was like the starting product is actually crystalline, but then the sheets which you get is amorphous, right? So do we know when this transition happened?
The sheets are also crystalline. I mean, they're crystalline in plane. Yeah, in plane, and I zoom past the X-ray diffraction, but you see diffraction peaks from the siloxane. So it's a crystalline material still, and there's in plane order. What ends up happening is that, like what I showed, is that the siloxane sheets are very, very unstable under the electron beam when you do TEM. And that will amorphize those. I think what's happening is the electron
this
beams
happens.
inducing oxidation.
Yeah, we also observe this in case of like orpiment. It's a very beam sensitive material. So if you put the beam, electron beam, or even, you heat the material, it just turns crystalline to amorphous within seconds. So I think this happens with these materials. Yeah, it's very common. Do you know what is the thickness of the sheets which you obtained? What is the thickness of the sheets?
they're not monolayers, so they tend to be 4 or 5 layers thick.
Okay. And what is the
Yeah.
aspect ratio we are talking about? What is the length?
It varies, but I think, when we do the sonication and we isolate with the centrifugation, the size is, changing, can be
Yeah.
up to a couple hundred nanometers.
Okay.
Fairly easily, and then the real small ones we can get down to like 50 nanometers.
Okay. Yeah. Thank you.
Yeah, thank you.